At 53 minutes past 2 in the morning Pacific time, a magnitude 5.7 earthquake struck the seafloor 138 kilometers west of the Oregon coast. 2 hours later, 3 more quakes followed off Northern California. Same plate boundary, same geological corner, the exact spot where 3 tectonic plates collide, and the fault that last destroyed the Pacific Northwest in 1700 has been quiet for 326 years. Nobody on the coast was hurt, nobody felt it strongly, and every seismologist who looks at this part of the world for a living woke up this morning with the same question, the one no instrument on Earth can answer. Is the cluster that just hit the West Coast a coincidence, or the first whisper of something we have been told for 3 centuries was coming? Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The morning the coast cracked. The first event came in at 53 minutes past 2 in the morning, Pacific time, June 3rd, 2026. The instrument that registered it sits in a hardened concrete vault on the campus of the University of California at Berkeley, but the wave it recorded had been travelling for less than a minute before it arrived there, racing inland at 4 kilometers per second from a point about 138 kilometers west-southwest of a small Oregon town called Pistol River. The Berkeley seismometer felt it. The seismometer at the Pacific Northwest Seismic Network's central facility in Seattle felt it. The instruments at the Humboldt Bay Observatory at the College of the Redwoods felt it. And within the same minute, automated systems at the National Earthquake Information Center in Golden, Colorado, were already calculating a magnitude. The number they came back with was a 5.7. That sounds modest. It is not. A magnitude 5.7 earthquake releases roughly the same energy as a tactical nuclear weapon. It happens, on the offshore margin where Oregon and California meet, about 2 or 3 times a year on average. Most of the time, when it happens out there, far enough from any town to be felt only as a faint roll that wakes a few light sleepers in Eureka or Crescent City, and that is the end of it. The seismologists log it, the local news mentions it the following morning if at all, and the planet goes on. This time, something different happened. Within the next 2 hours, 3 more earthquakes struck within 175 kilometers of the first one. One of them, at 12:45 Coordinated Universal Time, 64 kilometers west of a town in Humboldt County called Petrolia, came in at magnitude 5.08. The European Seismic Agency, looking at the same waveforms with their own algorithms, called it a 5.1. 26 minutes after that, a magnitude 4.47 struck almost exactly the same offshore location. Then, on the same plate boundary network, another moderate event further out to sea was logged. By the time the sun came up over the Cascade Range, 4 earthquakes of magnitude 4.5 or greater had occurred along a stretch of the Pacific coast that runs from the mouth of the Rogue River in Oregon down to the King Range Wilderness in California. All 4 were offshore. All 4 were inside the same complex of plates and faults, and none of them were inside the part of that complex that produces the kind of earthquake the rest of us have been told to be afraid of. That is the central thing to hold in your mind for the next 2 hours. The earthquakes that struck offshore Oregon and offshore California this morning did not happen on the Cascadia Subduction Zone, the locked fault that geologists and earthquake engineers have been studying for decades, the fault that broke last in January of 1700, and that is widely expected to break again in some future century, with consequences that would reshape the Pacific Northwest. The earthquakes this morning happened around that fault, on the small, internally deformed slab of oceanic rock that sits directly above the locked interface, on the transform boundary that runs east to west out to sea, on the spreading centre off the Oregon coast. They happened on every part of the system except the part everyone is watching, and that is why, in this video, I am not going to tell you that the big one is starting. The data does not say that. What the data does say is more subtle and more interesting and harder to dismiss. The data says that the place where 3 tectonic plates collide, the place at the southern end of the most dangerous fault on the west coast, just produced a pulse of activity that is at the upper edge of its normal range, in a geological moment when the fault next door has been quiet for 326 years, which is itself at the upper edge of how long that fault is supposed to stay quiet between failures. And the data also says that we do not, in this exact moment, have any way to tell whether what we just saw is the way these things normally go, or whether it is the way they go when something larger is about to happen. That uncertainty is not a scientific failure. It is the actual state of the field. And for the next 2 hours, I am going to walk you through what happened this morning, why the place it happened matters more than the size of what happened, what the historical record tells us about similar sequences, what it does not tell us, and what we should and should not conclude about the days and weeks ahead. I am going to take you down into the geometry of the Gorda Plate, which most people have never heard of, and which is the small piece of crust that holds the answer to everything that happened today. I am going to walk you through the 1992 Cape Mendocino earthquake, which is the closest historical analogue to the events this morning. I am going to take you back to the night of January 26, 1700, when the Cascadia fault last failed completely, because that is the clock against which all of this is being measured, and I am going to be honest with you about how the conspiracy theories are going to read this event over the next week, why most of them are wrong on the physics, and which 1 or 2 pieces of legitimate science get tangled up in those wrong readings. There is a particular kind of disorientation that comes from a morning like this one. The events do not produce a headline. They do not interrupt the news cycle. They do not show up on the front page of the regional paper because there is nothing photographic about them. No collapsed building, no panicked street, no helicopter footage of a coastline in distress. They show up only as a series of small dots on a USGS map and a few lines of text describing offshore epicenters in waters that have no inhabitants. And yet, if you are someone who has been paying attention to the slow accumulation of pressure on the Pacific Northwest Plate boundary system, the morning had the quality of a low hum that you have been hearing in the background of your life for a long time, briefly, suddenly, becoming audible. Not louder exactly, just more present. The clock that has been running for 3 centuries and a quarter became, for a few minutes between 3 and 6 in the morning Pacific time, just a little harder to ignore. That is the kind of event that does not get coverage in the way it deserves coverage. It does not produce a photograph. It does not produce a casualty count. The mainstream news will mention it briefly tomorrow, if at all, and the local broadcast outlets along the affected coast will run a short item with a stock USGS map graphic. And that will be the end of it for almost everyone outside the small community of seismologists and emergency preparedness planners who track this region for a living. The discrepancy between the scientific significance of the events and the public visibility of the events is the precise reason I am spending 2 hours of your time on this. It is not that the morning was dramatic in the conventional sense. It is that the morning was, in the strict scientific sense, a meaningful pulse on a system that the people who study it have been watching for decades, and the public-facing story of the morning understates the relevance of what happened by a factor that I would not be able to quantify but that I can say, with confidence, is large. Part 2, 3 plates, 1 corner. To understand why an earthquake off Pistol River and a cluster of earthquakes off Petrolia happening in the same morning matters, you need to know something about where those places sit on a map of the world. Not the political map, the tectonic one. The map of which pieces of the Earth's crust are moving against which other pieces, and how fast and in which direction. If you draw a line from the southern end of British Columbia down through Washington and Oregon and into Northern California, you're drawing one of the longest active plate boundaries on the planet. For most of that line, the boundary is what geologists call a convergent margin, a subduction zone, an oceanic plate called the Juan de Fuca Plate in the northern segments, and the Gorda Plate in the southern segments, is being shoved underneath the North American continent at a rate of about 3 or 4 centimeters every year. That is roughly the speed at which fingernails grow. It does not sound like much. Over a human lifetime it amounts to a few meters. Over a geological lifetime it amounts to entire mountain ranges, ocean basins, and the very shape of the world. That convergent boundary is what we call the Cascadia Subduction Zone. It runs for about 1,000 kilometers, from northern Vancouver Island in Canada down to a place off the coast of California called Cape Mendocino, and then, very abruptly at Cape Mendocino the geology changes, the Cascadia Subduction Zone ends. The boundary between the Pacific Plate and the North American Plate stops being a place where one plate is shoved beneath the other, and starts being a place where the 2 plates are sliding past each other horizontally. South of Cape Mendocino, the boundary is the San Andreas Fault. It runs from the Mendocino coast all the way down to the Salton Sea, 1,200 kilometers further south, and it does not subduct anything. It slips sideways. This transition does not happen smoothly. It happens at a corner, a geometric corner where three tectonic plates meet at a single point. The Pacific Plate, which makes up most of the floor of the Pacific Ocean, the North American Plate, which makes up the continent you're probably sitting on as you watch this, and a third plate, the smallest of the three, the one that has the highest fatality count per square kilometre of any tectonic plate on the planet, the Gorda Plate. The corner where these three plates meet is called the Mendocino Triple Junction. It is one of the most thoroughly studied points on the surface of the Earth, because it is one of the most active. It is also one of the most peculiar. Most triple junctions, the places where three plates meet, settle into a stable configuration where the three plates either spread away from each other or converge toward each other in a way that is geometrically consistent. The Mendocino Triple Junction is not like that. The three plates that meet there are doing three different things to each other. The Pacific Plate is pushing east, against the Gorda Plate, along a feature called the Mendocino Fracture Zone. The Gorda Plate is being consumed underneath North America, to the northeast, at the southern end of Cascadia. The Pacific Plate is sliding past North America to the south, on the San Andreas. And all of these motions are happening simultaneously, at the same geometric corner, in 3 dimensions, on a piece of crust that is geologically tiny. The piece of crust that has to absorb all of this is the Gorda Plate. And the Gorda Plate is the part of the story most people do not know, the part that explains why the earthquakes this morning happened where they happened, and why they matter the way they matter. So let me take a moment, here at the beginning, to introduce you to it properly. You will spend the next 2 hours hearing this name over and over. By the time we're done, the Gorda Plate is going to feel less like a piece of abstract geology, and more like a character in a slow-moving disaster. The plate gets its name from the Gorda Ridge, a spreading centre off the coast of southern Oregon, where new oceanic crust is constantly being formed by upwelling magma along a sub-sea volcanic line. The ridge runs roughly north to south, about 200 kilometres off the Oregon coast. Every year, the magma rising along the ridge adds a thin new sliver of basalt to the eastern edge of the Gorda Plate, and to the western edge of its sister plate, called the Juan de Fuca Plate, which lies north of the Gorda. The new basalt is hot and weak when it forms and cools and stiffens as it ages, the way iron behaves when you pour it into a mould. Over a few million years, the basalt that started at the ridge migrates eastward, becomes denser as it cools, and is eventually shoved underneath North America at the Cascadia Subduction Zone. The cycle of birth at the ridge and death at the subduction zone is one of the cleanest examples of plate tectonics in action anywhere in the world, and it has been running on the Pacific Northwest margin for at least 30 million years. The Juan de Fuca Plate and the Gorda Plate used to be a single tectonic feature called the Farallon Plate, which was an enormous oceanic plate that covered most of the eastern Pacific basin during the age of dinosaurs. Over the past 60 million years or so, the Farallon Plate has been progressively consumed underneath North America, with most of its original area now sitting deep in the mantle beneath the western United States as a slab of cold, dense rock that geophysicists can detect using seismic tomography. What remains of the original Farallon at the surface today is a small collection of fragments that includes the Juan de Fuca Plate, the Gorda Plate, the Cocos Plate off Mexico and Central America, and the Nazca Plate off South America. These fragments are the surviving children of a plate that used to be one of the largest tectonic features on the planet. The Gorda Plate is therefore not just small, it is the small remaining stub of something that used to be enormous, and the geometric stresses that act on it today are a consequence of the same tectonic process that has been consuming it for tens of millions of years. The plate is being eaten from the east while being formed from the west, and the relative rates of those two processes determine how fast the plate is shrinking or growing or staying the same size over geological time. At present, the eastern consumption rate is slightly higher than the western formation rate, which means the Gorda Plate is shrinking on average. Over the next few million years, in the absence of any other change in the regional tectonics, the Gorda Plate will eventually be entirely consumed, and the boundary between the Pacific and North American plates will become continuous along the entire length of what is now the Pacific Northwest. The earthquakes the Gorda Plate produces today are, in this very long view, the death throes of a small piece of oceanic crust that is gradually being absorbed into the planet. That is a long-term picture, and it does not directly bear on what happened this morning. But it does help explain why the Gorda Plate is internally so disturbed. The plate is being squeezed not just by the 3 present-day forces I described, but by the cumulative tectonic stress of millions of years of being progressively eaten from one side while being progressively formed from the other. The internal fault systems inside the plate represent the accumulated geological memory of that process. Some of those faults are millions of years old, some of them are still active, and some of them produce the earthquakes you heard about this morning. The Gorda Plate is the smallest named tectonic plate on the western North American margin. It measures roughly 200 kilometers north to south and 250 kilometers east to west. To put that in some perspective, it is about the size of South Carolina. Most of the major tectonic plates on Earth are continental in scale, with widths measured in thousands of kilometers. The Gorda Plate is smaller than a small American state, and it is being squeezed from three sides at once. The Pacific Plate is shoving it eastward, the North American continent is shoving it westward, and the Cascadia Subduction System is pulling its eastern edge down into the mantle. The result of those three forces acting on a piece of crust that's small is that the Gorda Plate does not behave like a rigid block. It buckles, it cracks internally, it fragments. Geologists have spent the last 40 years mapping the internal fault systems inside the Gorda Plate, and what they have found is that the plate is essentially a piece of broken glass, held together by gravity and friction, generating its own earthquakes inside its own body. That is the key fact for everything that follows. When most people imagine earthquakes off the Pacific Northwest coast, they imagine the Cascadia interface itself, the locked fault, the place where the Gorda Plate is being shoved underneath North America, where the two plates are stuck together, where strain is accumulating until the fault breaks loose in some future moment of catastrophic release. That fault is real, and that future moment is real, and we will get to it. But the earthquakes this morning did not happen there. They happened inside the Gorda Plate. They happened on faults that are entirely internal to that small fragmenting slab. They happened because the Gorda Plate is breaking itself apart from the inside out, the way a piece of glass breaks under three-sided pressure. That distinction matters because the kinds of earthquakes the Gorda Plate produces from its own internal deformation are not the kinds of earthquakes that can grow into a catastrophic full-margin Cascadia rupture. An internal Gorda Plate event of the size we saw this morning, magnitude 5.7, releases its energy on a single small fault inside the plate. It does not propagate onto the Cascadia interface. It does not unlock the locked patches. It is, in the strict mechanical sense, a different kind of event happening on a different kind of structure. The good news in this morning's data is that none of the four moderate earthquakes happened on the Cascadia interface itself. The harder news, the news that takes most of the rest of this video to unpack, is that the location and timing of these internal Gorda Plate events might not be entirely independent of what is happening on that locked interface a few tens of kilometers away. Part 3. The seismograms come in. Let me take you through what the seismologists actually saw this morning, in the order they saw it, because the sequence matters. At 10:53 Coordinated Universal Time, which is 3:53 in the morning local Pacific Daylight Time, the first arrival hit the broadband seismometer at Trinidad, California. Trinidad is the closest land-based station to the Mendocino Triple Junction, a small fishing town on a bluff above the Pacific about 30 miles north of Eureka. The Trinidad station is operated by the Berkeley Seismological Laboratory. It is one of about a dozen instruments in Northern California that report continuously to the United States Geological Survey's automated processing pipeline. When a P wave arrives at Trinidad, the pipeline starts a clock. It waits for the same P wave to arrive at the next station, and the next, and the next, and by the time the wave has been detected at 6 or 7 stations, the automated location algorithm has a preliminary epicenter, a preliminary depth, and a preliminary magnitude, which it pushes out to the public USGS feed within about 90 seconds. The location it came back with was 41.896 degrees north, 126.186 degrees west. If you look that up on a map, it places the epicenter about 86 miles offshore of the small Oregon town of Pistol River, which sits on Highway 101 in Curry County, the southernmost coastal county in Oregon. The depth came back at about 11 kilometers. The magnitude came back at 5.7. Within a minute and a half of the event, the German Research Center for Geosciences, which operates a parallel global earthquake location system out of Potsdam, had its own solution. They called it a 5.5. That kind of half-tenth magnitude discrepancy between two agencies looking at the same event in the first 90 seconds is completely normal. It reflects different algorithms making slightly different assumptions about the velocity structure of the crust in the source region. Over the following hours and days, the magnitude estimates will converge. The USGS will lock in a final magnitude after their seismologists have time to look at the long-period surface waves from stations all around the world, which give a more stable magnitude estimate than the high-frequency arrivals at nearby stations. The number it converges to will almost certainly be somewhere between 5.5 and 5.8. For the purposes of this video, I am going to keep using 5.7, because that is what the USGS has settled on as of the time I am putting this together, and because the precise value to within 1/10 of a magnitude unit does not change the story. About 90 minutes after the Pistol River event, at roughly 12:30 Coordinated Universal Time, the automated pipeline issued another preliminary report. This one was further south, about 64 kilometers west of Petrolia, California. Petrolia is a town of about 250 people in Humboldt County, sitting on the Mattole River near the King Range Wilderness. It has the distinction of being the closest settlement on the west coast to the Mendocino Triple Junction itself, which makes it the closest community on the continent to the most active triple junction in North America. The Petrolia event came in at magnitude 5.08. The European system, looking at the same waveforms, called it a 5.1. The two solutions agreed on magnitude within 0.02. On depth, however, they did not agree. The USGS automated solution put the depth at 0.15 kilometers, effectively at the seafloor. The European solution put it at 17 kilometers, which is a more typical depth for an offshore event in this region. That kind of depth discrepancy is also normal in the first hours after an offshore event, and it has nothing to do with anything mysterious. It has to do with the geometry of the seismic network. The seismometers that report to the USGS pipeline are all on land. They are spread along the coast from Trinidad up to Bandon, Oregon, and inland from Eureka to Redding. None of them are at sea. When you try to locate the depth of an offshore earthquake using only land-based instruments, you have what seismologists call a poor depth constraint. The mathematical inversion that produces the location is sensitive to the assumed velocity of seismic waves through the crust, and small errors in that assumption can produce large errors in the calculated depth. The fix, in the days after the event, is to relocate it using more sophisticated techniques that incorporate global station coverage and to constrain it against the depth distribution of nearby aftershocks. When that work is done in the next 24 to 72 hours, the Petrolia event will almost certainly be revised to a depth somewhere between 10 and 20 kilometers, which is the typical range for events in this part of the Gorda Plate. So if you go to the USGS website right now and look at the event details and you see a depth of 0.15 kilometers, I want you to understand exactly what you are looking at. You are looking at an algorithm doing the best it can with limited data in the first hour after an event. The number will be revised. The event itself is real. The location is real. The depth, as reported in the first few hours, is a placeholder. This is not a case of the government hiding anything. This is a case of automated systems being honest about the limits of what they can do without enough instruments in the right places. 26 minutes after the Petrolia 5.08, another event hit the same general location. This one was smaller, magnitude 4.47, also offshore Petrolia. The European agency saw it. The USGS catalogue logged it. The two solutions agreed on location and roughly agreed on size. And then, over the following hour, a fourth event further out to sea was registered. 4 earthquakes, 2 locations, 1 window of less than 3 hours, all offshore, all inside the Mendocino Triple Junction region, and the entire sequence happened while most of the people who live within 100 miles of those epicenters were asleep. Part 4. What it felt like, what it did not do. You might be wondering at this point whether anyone on the coast actually felt these earthquakes. The answer is yes, but not as dramatically as you might expect for events of this size. The Pistol River 5.7 was felt across a stretch of coast from Brookings, Oregon, down to about Eureka, California. The USGS Did You Feel It system, which collects shaking reports from civilian respondents in the affected area, logged about 300 reports within the first hour. Most of the reports were in the modified Mercalli intensity range of about 3 to 4, which corresponds to what scientists call light shaking. Hanging objects swaying, loose things on shelves rattling, a few people waking up, no reports of damage. The closest population centre, Brookings, Oregon, is roughly 150 kilometers from the epicenter, and at that distance the high-frequency seismic energy that does the most damage to buildings has attenuated to relatively harmless levels. What you feel instead is the longer period rolling motion of the surface waves arriving a couple of minutes after the initial shock. It is a sensation more than a violence. It is enough to wake you up. It is not enough to break things. The Petrolia events were similarly minor on land. Petrolia itself, the closest community, sits about 64 kilometres from the offshore epicenter, but it has a population of 250 people, and only a handful of them reported feeling the events. The shaking in Eureka, the nearest larger town, was reported at intensity 2 to 3. Most people who were awake at 12:45 in the morning local time did not notice anything. So in terms of immediate human impact, what happened this morning was a non-event for the public. No one was hurt, no buildings were damaged, no utilities went out, no services were disrupted. The fishermen at the harbour in Crescent City woke up at their normal hours and went out to their boats. The morning commuters on Highway 101 drove their normal commutes. If you had not been watching the USGS feed in real time, the only way you would have known anything happened at all is by reading about it on a regional news site, where it would have been the third or fourth headline behind something about the high school graduation or the state budget. This is one of the strange features of earthquakes at offshore locations of this magnitude. The events themselves are real. The energy released is real. The seismograms are unambiguous, but the surface effects on the populated coastline are minimal. You can have a 5.7 140 kilometres offshore and have the population on land barely register that anything happened. The reason that matters for the rest of this discussion is that the news coverage of these events tends to track surface effects rather than scientific significance. If a 5.7 hit downtown Eureka, you would be hearing about it for a week. Because it hit 140 kilometres offshore, in a place where there are no buildings and no people, you may not have heard about it before this video reached you, even though by every scientific measure, the morning sequence is the most interesting thing that has happened on the West Coast in weeks. There is one more thing I want to address before we get into the deeper structural picture. In the immediate aftermath of a moderate offshore earthquake on the Pacific Northwest margin, the standard institutional response involves an automatic evaluation by the National Tsunami Warning Center in Palmer, Alaska. The center looks at the location, the magnitude, the depth, and the mechanism, and runs an internal algorithm to decide whether a tsunami threat exists for the affected coast. For a magnitude 5.7 at the depth and offshore distance of this morning's event, the algorithm essentially always returns the same answer: no tsunami threat. The event is too small, too deep, and too distant from the populated coast to generate any seismic seafloor displacement that would produce a meaningful wave. The center logs the evaluation, the local emergency management agencies log the evaluation, and nothing further happens. There was no tsunami warning issued for the coast this morning. There was no advisory in effect. There was no reason to leave the beach, evacuate the harbour, or change any plans. The data is unambiguous on this point. I mention this because in the next few days, depending on how this morning's sequence gets covered in the social media ecosystem, you may see claims that there was some kind of suppressed tsunami advisory, or that the warning system failed, or that something is being hidden. I want to be clear with you in advance. There was no tsunami threat. The system functioned as designed. The events were not large enough or close enough to generate one. The absence of an advisory is not a cover-up. It is the correct scientific conclusion. The mechanics of tsunami generation are worth briefly understanding here, because the absence of a tsunami this morning is not just a fact about this morning's events. It is a fact about the kinds of earthquakes that can and cannot generate significant tsunamis along the Pacific Northwest coast. A tsunami is generated when an earthquake produces a sudden vertical displacement of the seafloor. The amount of water that gets displaced upward or downward by the seafloor motion sets the initial amplitude of the tsunami wave. To produce a meaningful tsunami, you need a large amount of seafloor displacement over a large area, which generally means you need a large magnitude earthquake on a shallow thrust fault that involves substantial vertical motion. The Cascadia interface, when it ruptures fully, produces exactly this kind of displacement. The 1700 event subsided the coastline by 1 to 2 meters and uplifted the offshore region by a comparable amount, and the resulting tsunami crossed the Pacific Ocean and arrived in Japan in less than a day. The earthquakes this morning produced essentially no vertical seafloor displacement. The Pistol River 5.7 was at a depth of 10 to 11 kilometers inside the Gorda Plate, on what appears to have been a steeply dipping internal fault, which means most of the slip on the fault was horizontal rather than vertical, and what little vertical motion did occur was at depth, and was not transmitted efficiently to the seafloor above. The petroleum events were similar in their mechanics. Neither event was large enough in magnitude nor of the right geometry to generate any meaningful tsunami. The National Tsunami Warning Centre's automated evaluation returned a negative result, which is what the system is designed to do for events of this size and type. The system did not fail. The system correctly concluded that there was nothing to warn about. The contrast with the December 2024 offshore Cape Mendocino 7.0 is instructive. That event was on the Cascadia interface itself, not inside the Gorda plate. It was on a thrust mechanism, which means it had vertical motion. It was large enough in magnitude that the algorithm's worst-case estimate triggered a precautionary warning. The warning was lifted within 90 minutes when the actual sea surface response was measured. The system was operating in exactly the way it is supposed to operate, erring on the side of issuing a warning when the algorithm's worst-case estimate justifies one, then revising the warning down to no threat when the data narrows the uncertainty. This morning's events did not even reach the threshold for the algorithm's worst-case estimate to trigger a precautionary warning. They were too small, on the wrong kind of structure, with the wrong kind of mechanism. The honest read is that the tsunami warning system has nothing to do with this morning's earthquakes, and the absence of any system activity is a feature, not a bug. Part 5. Why this part of the coast keeps cracking. Now we can return to the question that should really be on your mind by this point. Why did this happen here, today? To answer that, I have to take you down into the structure of the Gorda plate itself. Because the Gorda plate is not just a passive sheet of oceanic crust being shoved underneath North America, it is an actively deforming, internally faulting, geologically furious piece of rock, and it produces earthquakes at a rate that is among the highest of any small tectonic feature on the planet. The standard statistic calculated from the USGS catalogue since 1983 is that the immediate area around the Mendocino Triple Junction produces about 80 earthquakes of magnitude 3 or greater every year. That is a higher rate of seismicity than most subduction zones in the world. The reason has to do with the internal geometry of the Gorda plate and the three-sided stress field acting on it. Picture a piece of broken pottery, a flat dish that has been dropped on a stone floor and shattered, but the pieces are still roughly in the same relative positions. The broken edges along the cracks are not smooth. They are jagged, with countless small flaws and irregularities. If you were to push on one edge of the dish, the cracks would propagate further, and the rough edges of adjacent pieces would grind against each other, generating tiny pulses of sound and motion as they did. That is what is happening inside the Gorda plate. It is being pushed from three sides simultaneously, and the internal cracks that already exist are being made to slip against each other a fraction of a millimeter at a time. Each slip is an earthquake. The big slips, the ones that release enough energy to be measured at distant stations, are what we call moderate earthquakes. The little slips, the ones that happen every few hours on a continuous background, are what seismologists call microseismicity. The Gorda plate is making microseismicity constantly. It has been making it for as long as we have been listening. It will continue making it for as long as the geology lasts. The major internal fault systems inside the Gorda plate are oriented in two main directions. There is a set of faults that strike roughly north to south, parallel to the spreading centre off the Oregon coast where the Gorda plate is born, and there is a set of faults that strike roughly east to west, parallel to the Mendocino fracture zone where the Gorda plate meets the Pacific plate. Earthquakes inside the Gorda plate tend to happen on one or the other of these two fault sets. The Pistol River event this morning, based on the location and the depth and the rough direction of the first motion arrivals at nearby stations, was almost certainly on one of these north-south faults inside the northern part of the plate. The petroleum events were probably on a different structure further south, either on one of the east-west faults near the fracture zone or on a smaller internal break inside the southern Gorda. The reason it matters that these events happened on internal Gorda plate faults rather than on the Cascadia Subduction interface or on the San Andreas, is that the internal faults are mechanically isolated from the major locked structures. An earthquake inside the Gorda plate, on a north-south internal fault, does not propagate onto the Cascadia megathrust. The geometry is wrong. The Cascadia megathrust is a flat, shallowly dipping fault running underneath the North American crust. The internal Gorda faults are nearly vertical or steeply dipping, oriented at large angles to the megathrust. A rupture on one cannot turn into a rupture on the other, in the way that, for example, a rupture on the southern San Andreas can propagate from one segment to the next. What internal Gorda plate earthquakes can do, however, is transfer stress. When a fault inside the Gorda plate slips, it redistributes the stress field in the surrounding rock. Some patches that were close to failure end up further from failure because the slip has relieved the load on them. Other patches that were further from failure end up closer to it because the slip has loaded them. This is called Coulomb stress transfer, and it is one of the most studied effects in modern seismology. The stress changes are small, usually a fraction of a megapascal at most, but they can be enough to nudge a fault that was already close to failure into failing earlier than it otherwise would have. The Coulomb framework was developed in the 1990s and refined through the early 2000s by a research group led by Ross Stein at the United States Geological Survey, Jeff King at the Institut de Physique du Globe in Paris, and Shinji Toda of Tohoku University in Japan. The premise is that earthquakes do not occur randomly. They occur on faults that have been brought close to failure by the slow tectonic loading of plate motions, and the precise moment of failure can be modulated by relatively small additional stress changes from nearby events. When a fault slips, the rock around it redistributes its stress field in a way that can be calculated mathematically using the elastic properties of the crust and the geometry of the slipping fault. The resulting stress map shows lobes of increased loading and lobes of decreased loading radiating outward from the source. Faults that sit inside the lobes of increased loading have their effective failure stress reduced, which means they can fail at a lower level of accumulated strain than they otherwise would have required. Faults that sit inside the lobes of decreased loading have their effective failure stress increased, which means they can absorb additional strain before failing. The framework has been applied retrospectively to many large earthquake sequences and has been broadly successful at explaining where and when aftershocks occur, and at predicting which adjacent faults are more or less likely to fail in the months and years after a major event. Applied to this morning's events at the Mendocino Triple Junction, the Coulomb framework would say that the Pistol River 5.7 has produced a small but calculable change in the stress field across the surrounding region, parts of the Cascadia interface immediately east of the rupture, parts of the Pacific Plate to the south of the rupture, and parts of the Gorda Plate itself further north and south of the rupture have all had their stress states modified by some small amount. The published Coulomb stress calculations for events of this magnitude at this kind of geometry typically produce maximum stress changes on the order of 1/10 of a bar to a few bars, at distances of a few tens of kilometers, decaying with distance roughly as the inverse cube. By the time you get to 50 or 100 kilometers from the source, the stress change is on the order of 1/100th of a bar or less. Whether that is enough to matter for failure on the affected faults depends entirely on how close those faults were to failure already. What that means for this morning's events is that the Cascadia interface, which sits just east of the Gorda Plate at the southern end of the subduction zone, is now in a slightly different stress state than it was 12 hours ago. The Pistol River 5.7 and the Petrolia cluster have redistributed the stress field in the southern Gorda region by some small measurable amount. The most likely effect is essentially nothing. The most likely outcome is that the Cascadia interface continues to load slowly under the same long-term motion of the Pacific Plate system, and the morning's events become a footnote in the regional catalogue. But there is a smaller, non-zero possibility that the stress transfer has nudged some part of the southern Cascadia interface fractionally closer to failure. That possibility is not large. It is not the kind of probability that justifies emergency response. But it is not nothing either, and the honest reading of the data has to acknowledge it. The honest reading also has to acknowledge an important asymmetry in how Coulomb stress transfer works at the Mendocino Triple Junction specifically. The geometry of the southern Cascadia interface is complex enough that the stress transfer calculations from a Gorda Plate internal event to the locked interface beneath North America are not easy to do precisely. The dip of the interface in this region, the depth of the locked patch, the orientation of the slipping fault inside the Gorda Plate, all of these factors interact in ways that mean the calculated stress change at any given point on the interface can vary by an order of magnitude depending on the modelling assumptions. The published literature has not, as of the time I am putting this video together, produced a definitive Coulomb stress map for the morning's events. That work will be done in the academic time frame of weeks to months, not in the public time frame of hours to days, and by the time it is published, the practical relevance of the calculation may have been overtaken by whatever actually happens next on the system. There is a related framework that came out of the wake of the 2011 Tohoku earthquake, in a paper by Toda, Stein and Lin published shortly after the event. The paper used Coulomb stress transfer calculations to identify which adjacent fault segments in Japan had been brought closer to failure by the Tohoku rupture, and the paper found that several of those segments were close enough to failure that future events on them were materially more probable than they had been before. The framework has since been applied to other large subduction zone events in Chile, in Sumatra, and along the Aleutian Arc, with varying degrees of success. The lesson from that body of work is that Coulomb stress transfer is a real effect, that it operates over distances of tens to hundreds of kilometers from the source, and that it can produce statistically detectable shifts in the rates of future earthquakes on adjacent structures. The framework does not predict specific events. It modifies the probabilities of those events in ways that are sometimes large enough to matter for hazard assessment, and sometimes too small to be operationally useful. Part 6. 1992. To understand what an active sequence at the Mendocino Triple Junction can look like when it really gets going, you have to know about what happened at this same place on the 25th and 26th of April in 1992. It is the most directly comparable event in the historical record, and it is the event that I am holding in my mind as the reference frame for everything I am telling you this morning. The 1992 Cape Mendocino earthquake sequence began at 11:06 in the morning local time on April 25th, when a magnitude 7.2 earthquake struck about 24 kilometers east of Cape Mendocino. Unlike this morning's events, which were on internal Gorda Plate faults, the 1992 main shock was a thrust earthquake on the Cascadia Subduction interface itself. It was, in essence, a partial failure of the southernmost part of the Cascadia locked zone. It produced strong shaking from Crescent City down to San Francisco. 500 buildings were damaged. About 100 people were injured. A fire broke out in Scotia, California, that destroyed several buildings. The town of Petrolia, the same town that sits closest to this morning's offshore events, was at the epicenter, and almost every structure in town suffered some damage. The 7.2 was unusual in itself. It was, at the time, the largest thrust earthquake to have occurred in the contiguous United States on a subduction interface in the instrumental era. It was a small partial rupture of the southernmost segment of Cascadia, the segment that, in the 1700 event, ruptured along with the rest of the margin from California up to Vancouver Island. The fact that the 7.2 did not propagate north along the rest of the interface, that it remained confined to the southernmost segment, is one of the reasons we know that Cascadia can rupture in pieces rather than always going all at once. What happened next is the part that matters for this morning. 18 hours after the 7.2, at 7:41 in the morning on April 26th, a magnitude 6.5 earthquake struck offshore, about 30 kilometers west of Cape Mendocino. This event was on the Pacific Plate, not the Cascadia interface. It was a strike-slip event on a transform fault inside the Pacific Plate, triggered by the stress transfer from the main shock the previous day. 3.5 hours later, at 11:18 in the morning, a magnitude 6.6 struck almost the same offshore location. 2 strike-slip events on the Pacific Plate, in just over 3 hours, both triggered by the main shock on the Cascadia interface 18 hours earlier. The 1992 sequence is the textbook example of how a single earthquake at the Mendocino Triple Junction can transfer stress across multiple plate boundaries and produce a cascade of follow-on events on adjacent structures. The 7.2 redistributed the stress field, and the parts of the Pacific Plate that were closest to failure responded by failing, releasing their own accumulated stress on their own internal faults. The cascade did not continue further. There was no subsequent major event on the Cascadia interface. There was no large event on the northern San Andreas. The sequence dissipated within a few days. What I want you to notice, however, is that the 1992 sequence went in the opposite direction from this morning. The 1992 event started with the largest event, the 7.2 on the Cascadia interface, and then triggered smaller events on adjacent structures. This morning's event started with a 5.7 on an internal Gorda fault, and have so far produced only smaller events on adjacent structures. There has been no triggering of a larger event on the locked Cascadia interface. There has been no propagation onto the San Andreas. The cascade, if it is a cascade, is going in the small direction rather than the large direction. This is one of the things that argues against the foreshock interpretation of this morning's data. In foreshock sequences globally, the typical pattern is accelerating activity. The seismicity rate increases, the maximum magnitude increases, The events get closer in time as you approach the main shock. This morning is the opposite of that pattern. The largest event came first. The subsequent events are smaller. The seismicity rate is not accelerating. By the time I am putting this video together, the rate of new events in the region has dropped back to roughly the baseline. There is another comparison that is worth pulling forward here, which is the December 2024 offshore Cape Mendocino earthquake. On December 5th of that year, a magnitude 7.0 struck about 60 kilometers west-southwest of Ferndale, California, at a depth of 10 kilometers. The event was felt across Northern California into the San Francisco Bay Area, and it triggered an immediate tsunami warning for the affected coast. The warning was cancelled within 90 minutes when sea level observations from coastal tide gauges confirmed that no significant wave had been generated. The 2024 event was, in essence, a smaller version of the 1992 7.2. It was a thrust event on the Cascadia interface at the southernmost segment. It happened in the same general location, and it dissipated, like the 1992 event, without triggering anything larger on the rest of the Cascadia margin or on the San Andreas system. The seismicity rate at the Mendocino Triple Junction returned to baseline within several months. By the spring of 2026, the regional catalogue was not visibly different from what it had been before December of 2024. The 2024 event is the most recent example of a moderate to large earthquake at the Mendocino Triple Junction, failing to produce any larger cascade. It is one of the data points in the baseline most likely interpretation of this morning's events. The 2024 event is also a useful reminder of how the tsunami warning system responds to events of this size and depth in this region. The automated NTWC algorithm, applied to a 7.0 at 10 km depth on a thrust mechanism on the Cascadia interface, returned a tsunami warning. The warning was real. It was distributed through the emergency alert system. It was lifted within an hour and a half once the actual sea surface response was measured at coastal tide gauges, and the threat was confirmed to be smaller than the algorithm's worst-case estimate. The 2024 episode is the textbook example of the warning system functioning as designed, erring on the side of issuing a precautionary warning, then cancelling that warning once the data narrows the uncertainty. The contrast with this morning is informative. This morning's events were too small and on the wrong kind of structure to trigger a warning at all. The system did not warn anyone, did not need to warn anyone, and the absence of a warning is the system functioning correctly, not the system failing. But, and this is the careful caveat I have to add, foreshock sequences are not always neat. The 2011 Tohoku earthquake off Japan, which I've talked about on this channel before in the context of the Artemis radiation discussions and the Japan Trench thread, had a foreshock sequence that included a magnitude 7.3 foreshock approximately 51 hours before the magnitude 9.1 main shock. The 7.3 did not look, at the time, like a foreshock. It looked like a moderate offshore event. It did not have an obvious accelerating tail. The seismicity rate in the hours after the 7.3 did not look obviously different from the baseline. It was only after the 9.1 that the 7.3 was retroactively classified as a foreshock. The historical record of foreshock sequences is full of events that, in real time, looked exactly like routine moderate earthquakes, and that only acquired their significance in retrospect. So the 1992 analogue tells us two things at once. It tells us, on one hand, that moderate sequences at the Mendocino Triple Junction can stay confined and dissipate without producing anything larger, which is the historical expectation, and which is what is most likely to happen with this morning's events. And it tells us, on the other hand, that the absence of an obvious foreshock signature does not, by itself, rule out the possibility that this morning's sequence is a foreshock to something larger. That is the uncomfortable middle position. Most likely nothing, not impossibly something. There is one more 1992 detail that is worth mentioning. The 7.2 main shock generated a small tsunami, with a maximum run-up of about a metre along the immediately adjacent Humboldt County coast. The tsunami was not catastrophic, but it was real, and it was the first instrumentally observed tsunami in the Pacific Northwest in the modern era. The tide gauges at Crescent City and Humboldt Bay recorded the wave train clearly. The data from those measurements has been used in the subsequent decades to calibrate the tsunami models that the National Tsunami Warning Center now uses to evaluate threats from Cascadia events. In a sense, the 1992 earthquake was the test event that the warning system has been trained on for the past 30 years. The system that did not issue a warning for this morning's events did not issue one because the morning's events were not the kind of events that the test data showed could produce a meaningful wave. The 7.2 of 1992 could and did. A 5.7 inside the Gorda plate could not and did not. That is the line that the modern warning system draws, and it draws it based on real observations from real events. The other 1992 detail that is worth noting is what happened in the months and years after the sequence dissipated. The southern Cascadia margin returned to its normal background activity within a few weeks. The aftershocks decayed according to a standard Amori law pattern, with the rate dropping by roughly a factor of 10 every order of magnitude in time after the main shock. By the end of 1993, the regional catalogue was back to baseline. There was no subsequent escalation. There was no precursor signal that retrospectively identified the 7.2 as a foreshock to a larger event. The 1992 sequence stood alone in the historical record as a moderate to large event that did not lead to anything bigger. It is one of the central data points in the case for treating this morning's smaller events as also most likely standing alone. The historical record contains many more examples of moderate Mendocino sequences that dissipated without consequence than it contains examples of moderate sequences that turned out to be foreshocks. The probability weighting reflects that imbalance. Part 7. 326 years. To explain why the middle position is uncomfortable rather than reassuring, I have to take you back in time, back to the night of January 26, 1700. The night the Cascadia Subduction Zone last failed completely. We know it happened on that night to within a few hours. The level of precision is remarkable for an event that predates instrumental seismology by more than 2 centuries. We know the date because of 2 independent lines of evidence that agree. The first is the Japanese tsunami record. The Edo period tax records from coastal villages along the Pacific coast of Japan describe a tsunami that arrived on the morning of January 27, 1700 local Japanese time. The tsunami was unusual because it was not preceded by any felt earthquake in Japan. There was no source visible from Japan. The Japanese authorities at the time did not know where the wave came from. They called it the orphan tsunami because it had no parent. The records describe wave heights, damaged rice fields, destroyed coastal salt works. The records were preserved in village archives for 300 years before anyone connected them to a source. The second line of evidence comes from the Pacific Northwest itself. The night of the 1700 earthquake produced enormous subsidence along the coast, from Vancouver Island down to northern California. Entire stretches of coastal forest dropped by 1 to 2 meters in a few minutes as the upper plate of the subduction zone shifted seaward. The trees that had been standing on dry land found themselves below the high tide line. Salt water killed them. Over the following decades and centuries, the dead trees decayed. The soil was buried under tidal sediments, and the stumps and rooted bases were preserved underground as what geologists call ghost forests. In the 1980s and 90s, several research teams led by Brian Atwater of the USGS and Kenji Satake of the University of Tokyo independently identified these ghost forests, dated the outermost growth rings using radiocarbon and tree ring analysis, and matched the date to the Japanese tsunami record. The match was exact. The same event that submerged the Pacific Northwest coastline produced the orphan tsunami that arrived in Japan less than a day later. There is also a third line of evidence that has emerged more recently, and that is worth knowing about. The indigenous peoples of the Pacific Northwest, including the Makah, the Quiluta, the Yurok, the Hoopa, the Tolowa, and the various Salish-speaking nations of southern British Columbia, all carry oral traditions describing the night of January 26, 1700, in remarkable detail. The traditions describe villages on the coast that were swept away by enormous waves, canoes carried inland into the forest by water that came in after a violent shaking, and survivors who moved to higher ground in the immediate aftermath. The detail in these traditions is consistent enough across the affected geography, and consistent enough with the geological and Japanese records, that the academic literature now treats them as a primary source of information about the 1700 event. Ruth Ludwin, a former research scientist at the University of Washington, published several papers in the early 2000s cataloguing these oral traditions and matching their geographic distribution to the modelled tsunami inundation patterns from the 1700 rupture. The match is striking. The communities whose oral traditions describe the largest waves are the communities at locations where the modelled tsunami would have produced the largest run-ups. The communities whose oral traditions describe lesser effects are at locations where the modelled run-ups would have been smaller. The three lines of evidence, Japanese, geological and indigenous, converge on the same event with the same date and the same magnitude. The convergence is important because it means we know quite a lot about what the 1700 event was, even though we have no instrumental record of it. We know its date, we know its approximate magnitude, we know its rupture extent, we know its tsunami amplitude at the source and at distant locations across the Pacific. We know its onshore effects in terms of coastal subsidence. What we do not know, and what no source can tell us, is what the days and weeks leading up to the event looked like in terms of smaller seismicity. The geological record is event resolving but not pattern resolving. The oral traditions describe the night of the event but do not preserve detail about the preceding period. The Japanese tax records date the tsunami arrival but contain no information about the source region. The state of the Cascadia margin in the days before January 26, 1700 is a piece of history that has been lost. The magnitude of the event has been estimated through the area of the rupture, the amount of subsidence at the coast, and the amplitude of the tsunami at Japanese tide gauge sites. The estimates converge on something in the range of magnitude 8.7 to magnitude 9.2. The event was almost certainly a full margin rupture, with slip on the Cascadia interface from the northern end near Vancouver Island, all the way down to the southern end near Cape Mendocino. Or at least it ruptured most of that distance. There is some ongoing debate about whether the southernmost segment, the segment immediately adjacent to the Mendocino Triple Junction, fully participated in the 1700 event, or whether it ruptured in a partial event sometime later. The point for this morning's discussion is that the last time the Cascadia interface failed completely was on the night of January 26, 1700. As of the morning of June 3, 2026, that is 326 years and 4 months ago. 326 years of strain accumulation. 326 years of the Gorda Plate slowly grinding underneath North America, while the interface remains locked and bends and stores elastic energy like a steel spring being slowly compressed. The question of how long that interface can remain locked before it has to fail again is the central question of Pacific Northwest seismic hazard, and the answer, based on the paleoseismic record, is that it depends on which segment you are asking about and which kind of failure you mean. The most thorough work on Cascadia recurrence intervals was done by Chris Goldfinger at Oregon State University, working with sediment cores collected from the deep ocean floor along the length of the Cascadia margin. The cores contain layers of what geologists call turbidites, which are sediment deposits produced when an earthquake shakes the continental shelf and causes underwater slope failures. The slope failures send slurries of sediment racing down the continental slope and out across the abyssal plain. Each major earthquake produces a turbidite. Each turbidite gets buried by ordinary background sedimentation over the centuries that follow. By counting turbidites in a core and dating them using radiocarbon, you can build a chronology of major earthquakes along the Cascadia margin going back 10,000 years. The Goldfinger chronology identifies 41 earthquakes in the past 10,000 years along the Cascadia margin. Not all of those 41 were full margin events. Some were full margin, some were partial ruptures of the northern segments only, some were partial ruptures of the southern segments only. When you separate the catalogue into full margin events versus partial events, you get different recurrence intervals. The full margin events have an average recurrence interval of about 500 to 600 years. The southern segment events, which are the ones immediately relevant to what is happening at the Mendocino Triple Junction this morning, have a shorter average recurrence interval, in the range of 200 to 530 years. What this means for the southern segment specifically is that the 326-year quiescence we are currently in is well within the range of recurrence intervals observed in the paleoseismic record. We are not yet past the average, we are not yet at the historical maximum, but we are at a stage where, if you treat the paleoseismic record as a probability distribution, the probability that the next event is closer than half the average recurrence interval is no longer especially comforting. The United States Geological Survey, in their National Seismic Hazard Model, estimates a roughly 10% probability of a full margin magnitude 9 or greater Cascadia rupture in the next 50 years. That number incorporates the paleoseismic record and the current state of strain accumulation as measured by GPS. The Oregon Office of Emergency Management uses a different framing and estimates a roughly 37% probability of a magnitude 7.1 or greater rupture on some part of the Cascadia system in the next 50 years. The two numbers are not in tension. The lower number is for the largest possible event. The higher number is for any event large enough to cause significant damage somewhere along the margin. What none of these numbers can tell you is when, within those 50 years, the rupture will happen. The probability of a rupture in the next year is approximately 1/5 of 1%, if you average the next 50 years and assume the probability is constant across that window. The probability of a rupture in the next week is essentially 0 on the same averaging assumption. These are not the kinds of numbers that justify changing your morning routine. But they are also not 0, and the 326-year clock is real, and the Mendocino Triple Junction just produced a moderate earthquake sequence on the same plate boundary system that will produce the next Cascadia rupture, whenever that rupture comes. The way the Goldfinger turbidite work actually arrived at these numbers is worth describing in more detail, because the methodology is what gives the numbers their weight. The technique involves drilling sediment cores from the deep ocean floor along the continental slope offshore of Cascadia, in water depths of several thousand meters. The cores are typically a few meters long, and capture the most recent 20 to 30,000 years of sediment deposition. Within those cores, two kinds of layers can be identified. The background layers are made of hemipelagic mud, the slow accumulation of fine sediment that settles out of the water column over centuries to millennia. The turbidite layers are made of coarser material, sand and silt mixed with organic debris, deposited in a single rapid event when a submarine slope failure released a slurry of sediment onto the abyssal plain. The turbidites can be distinguished from the background hemipelagic mud by their grain size, their internal structure, and their geochemistry. They are the geological fingerprints of major earthquakes that shook the continental slope hard enough to trigger underwater landslides. The radiocarbon dating of the turbidites is the part of the work that takes the longest. Each turbidite is dated by extracting fragments of organic material from the immediately overlying hemipelagic sediment, which establishes a maximum age for the turbidite. Cross-referencing the dates from multiple cores collected at different locations along the margin allows the same turbidite to be identified in different cores, which provides a measure of how far along the margin the original earthquake's effects extended. Turbidites that appear in cores from the entire length of the margin, from offshore Vancouver Island down to offshore Cape Mendocino, are interpreted as full margin events. Turbidites that appear only in the southern cores, but not in the northern ones, are interpreted as partial ruptures of the southern segment. The methodology was refined through the 1990s and early 2000s, and the resulting chronology has been independently verified by other research groups using different sampling strategies and different analytical techniques. The 41 event count in the past 10,000 years is now widely accepted as the best available estimate. When the chronology is broken down into full margin events versus partial events, the full margin events come out to approximately 19 in the past 10,000 years, with the most recent being the 1700 event. The average recurrence interval for full margin events is therefore approximately 530 years, with substantial variance. Some intervals are as short as 200 years, some are as long as 1,000. The 1700 event followed a previous full margin event by approximately 780 years, which is at the long end of the historical range. The interval since 1700, 326 years and counting, is well within the historical range and is shorter than several historical intervals between full margin events. On the full margin recurrence metric, we are not yet at a statistically alarming time. When the chronology is filtered for partial southern segment events, the picture changes. Partial southern events appear more frequently than full margin events, with average recurrence intervals in the range of 200 to 300 years for the southernmost segment. The southern segment can rupture by itself, as it did in the 1992 7.2, and the partial events accumulate stress that gets released along with the rest of the margin in subsequent full margin events. The partial events are smaller, magnitude 8 to magnitude 8.5, rather than the magnitude 9 of the full margin events, but they still produce significant shaking along the southern Oregon and northern California coast, and they still generate tsunamis. The 326-year quiescence on the southern segment specifically is therefore in the upper portion of the historical range for partial southern events, even though it is well within the range for full margin events. The distinction between the full margin and partial southern timelines is important, because it changes how the morning's events should be interpreted. If you're thinking about a future full margin rupture, the morning's events are happening at a time when the clock is roughly 2/3 of the way through the average recurrence interval, which is to say, not yet at the average and not in any urgent zone. If you're thinking about a future partial southern rupture, the morning's events are happening at a time when the clock is closer to the average for the southern segment, which is to say, in the zone where the next event becomes increasingly probable with each passing year. The morning's events are happening at the southern end of the Cascadia system. They are not by themselves an indicator of an imminent full margin rupture. They are, however, happening on the segment that has the shorter recurrence interval, and that is the segment on which the next significant event is most likely to occur, all else being equal. Part 8. What it would look like if it were a foreshock. I have been careful, in this video so far, to keep both interpretations open. The most likely reading of this morning's data is that the events were routine elevated baseline activity at the Mendocino Triple Junction, that they will dissipate over the next few days, and that nothing larger will follow. The less likely reading is that they are an early stage of something larger, preparing to rupture on the Cascadia interface or one of the major structures associated with the Triple Junction. I want to spend a few minutes here on what the second reading would actually look like if it were happening, because the distinction between the two readings is not always made carefully in public discussion, and because there are specific things to watch for that would tilt the interpretation toward the second reading. A foreshock sequence preceding a major earthquake typically has several recognizable features. Not all foreshock sequences have all of these features, but most have at least 2 or 3. The first feature is accelerating event rate. In the hours or days before a main shock, the rate of small earthquakes in the source region increases. The increase is often gradual, sometimes only detectable in retrospect, but in the clearest cases it can be dramatic. The 2011 Tohoku sequence showed a clear rate increase in the 48 hours before the main shock, with the 7.34 shock acting as the most visible single event in a broader pattern. The 2010 El Mayor Cucapa sequence in northern Mexico showed a months-long rate increase before the main 7.2 rupture. The current rate at the Mendocino Triple Junction, in the hours since the Pistol River event, has dropped back to baseline. There is no accelerating signal. The second feature is increasing maximum magnitude. In a typical foreshock sequence, the largest event before the main shock is itself part of a sequence that has been building in magnitude. The Tohoku 7.34 shock was the largest in a sequence of events that had been escalating over the prior 2 days. This morning is the opposite. The Pistol River 5.7 was the largest event, and everything since has been smaller. The pattern is main shock aftershock, not foreshock main shock. The third feature is spatial migration. Foreshock sequences often show events migrating toward the eventual main shock epicenter. The events get progressively closer in space to the location where the main rupture will start. The 2011 Tohoku foreshocks migrated north along the Japan Trench toward the eventual main shock nucleation point. This morning's events have a complex spatial pattern. The Pistol River epicenter is to the north, the Petrolia events are to the south, and the fourth event is further out to sea. There is no clear migration in any direction. The pattern looks more like simultaneous activation of multiple independent structures than like a progression toward a single location. The fourth feature is depth shoaling. In some foreshock sequences, the events get progressively shallower as the main shock approaches. This is not universal and is debated in the literature. This morning's events are all at depths consistent with the typical depth range for the region, around 10 to 20 kilometers, and there is no clear depth pattern. The fifth feature, which is less specific but more diagnostic, is what seismologists call slow slip activity. In some major subduction zone events, the main shock is preceded by a slow slip event on the deeper portion of the interface. The slow slip event is not felt at the surface, but it is detectable through GPS measurements of crustal motion at coastal stations. The southern Cascadia margin, as I mentioned earlier, and as discussed in our May 9th video on the Crescent City offshore activity, has been having an active episodic tremor and slip episode on the deeper interface for several weeks in the spring of 2026. The Pacific Northwest Seismic Network identified 153 tremor epicenters on the southern Cascadia margin during the May 9th window. Whether the current episode is still active, and whether this morning's offshore events relate to it, is the kind of question that will be addressed in the academic literature in the coming months, but is not resolvable in real time. Putting all 5 features together, The assessment from the publicly available data is that this morning's events do not look like a textbook foreshock sequence. They look like a moderate, somewhat clustered, more or less baseline event sequence at an already active region. The most likely reading is routine, but there is a piece of the historical record that has to be acknowledged here, because it is the piece that prevents anyone honest from dismissing the foreshock interpretation entirely. We do not know what the days and weeks before January 26, 1700 looked like in seismic terms. There were no instruments. There were no observers writing down the small earthquakes that happened in coastal Oregon or California in the months before the Great Rupture. The historical record is essentially silent on the question. The Cascadia interface has not produced a full margin rupture in the instrumental era. We do not know, with confidence, what the foreshock pattern of a Cascadia rupture would look like. We are using analogues from other subduction zones, from Tohoku and Sumatra and Chile, to guide our interpretation of what we are seeing at Cascadia. Those analogues may be relevant, they may not be. The honest answer is that we will find out which one is correct only when the next Cascadia rupture happens, and by then it will be too late for the question to matter, except in retrospect. There is also a statistical effect worth pulling out here, called the foreshock recognition problem, that explains why the absence of a textbook signal is not as reassuring as it sounds. The statistical literature on global foreshock identification, going back to the work of David Jackson and Jan Kagan at UCLA in the 1990s, and continuing through more recent papers by Karen Felser at the USGS, has consistently shown that the most common type of foreshock sequence is one that cannot be distinguished in real time from an ordinary moderate earthquake. Most events that turn out to be foreshocks did not look like foreshocks while they were happening. The accelerating rate signature, the increasing magnitude signature, the spatial migration signature, all of these are characteristics of a subset of the historical foreshock catalogue. The other subset, which is the larger fraction, consists of foreshocks that arrived as single moderate events, followed by a quiet interval and then a main shock. The 2011 Tohoku case is in this larger fraction, in the sense that the 7.3 foreshock did not have an obvious accelerating tail. There was a brief flurry of small aftershocks, and then a quiet day, and then the magnitude 9.1. The implication for this morning is uncomfortable but worth being clear about. The fact that the morning's events do not have an obvious foreshock signature is not evidence that they are not foreshocks. It is evidence that, if they are foreshocks, they belong to the larger and more common subset of foreshock sequences, the subset that does not announce itself. The absence of a textbook pattern does not raise the probability of the foreshock interpretation back to something high. The base rate is still around 5%, but it does mean that the careful posture is not to look at the missing accelerating tail and conclude that the foreshock interpretation has been ruled out. It has not been ruled out. It has been left in approximately the same condition it was in before we looked. This is one of the ways in which honest seismology is harder than confident seismology. The data does not give you a clean signal. It gives you a probability distribution that is mostly weighted toward routine and has a small but real tail weighted toward catastrophic, and the work of interpretation is to live in that distribution without collapsing it to either extreme. The morning's events are inside the distribution. They have not moved the distribution very much, they have not moved it towards zero, and they have not moved it towards certainty. They have moved it slightly toward the right tail. By how much? No one can quantify precisely. That is the honest position. It is the only position the data supports. Part 9. What the geologists who study this for a living are actually thinking. I want to be careful here, because the question of what the seismologists who study Cascadia actually think about events like this morning's is sometimes mischaracterized in public discussion, and the misrepresentation tends to run in both directions. There are voices on the internet who claim that the seismologists are sure the big one is imminent and are hiding that conclusion from the public. There are other voices who claim that the seismologists are dismissive of all foreshock interpretations and are intellectually closed to the possibility that anything significant is about to happen. Neither of those positions reflects the actual scientific community, which is much more interesting and more honest than either caricature. The actual position, as best I can characterize it from the published literature and from the public statements of researchers at the USGS Pacific Coastal and Marine Science Center, the Pacific Northwest Seismic Network, the Oregon Department of Geology and Mineral Industries, and the Berkeley Seismological Laboratory, is roughly as follows. First, the Cascadia interface is in an actively loading state, and has been for the entire instrumental period. Strain is accumulating at a rate that is reasonably well constrained by GPS measurements at coastal stations. The locked portion of the interface is storing elastic energy that will be released eventually in a major rupture. The timing of that rupture is the central unknown. Second, the southern segment of the interface near the Mendocino Triple Junction has unique geometric and frictional properties that distinguish it from the rest of the margin. The interface in this region transitions from a clear subduction geometry in the north to a more complex set of fault interactions as it approaches the Triple Junction. The southern segment can rupture in partial events, as it did in the 1992 Cape Mendocino 7.2. It can also participate in full margin events, as it did in 1700. Whether the next major event will be a partial southern event or a full margin event is unknown. Third, moderate seismicity around the Mendocino Triple Junction is the rule rather than the exception. The region produces magnitude 5 and greater events at a rate of 2 to 3 per year. Most of these events do not have any larger consequence. They are part of the ongoing internal deformation of the Gorda Plate and the routine activity of the Pacific Plate transform boundary. Fourth, when a sequence of 2 or more moderate events occurs in a tight time window, as happened this morning, the response among working seismologists is increased attention rather than alarm. The probability of the sequence being a precursor to a larger event is small but non-zero. The most common practical response is to look for the diagnostic features I described in the previous part: accelerating rates, increasing magnitudes, spatial migration, depth changes, slow slip signatures. If those features develop in the days that follow, the assessment shifts. If they do not, the sequence is reclassified as routine and the catalogue moves on. Fifth, and this is the part that is most often missing from public discussion, the working seismologists in this region operate under significant scientific humility about their ability to forecast events. The track record of short-term earthquake prediction, globally, is one of nearly uniform failure. The single major success story, the prediction of the 1975 Haicheng earthquake in China, was followed by the catastrophic failure to predict the 1976 Tangshan earthquake in the same general region a year later, despite extensive monitoring. The Haicheng-Tangshan pair is the foundational lesson in the limits of operational earthquake prediction. The lesson is that even when you think you have identified the precursors, and even when you have the political will to act on them, the next event in the same kind of regional context can fail to produce any recognizable precursors and can catch the monitoring system completely by surprise. This is not a position of nihilism. The seismologists who study Cascadia have learned a great deal in the last 40 years. They know the location of the locked interface in detail. They know the rate of strain accumulation. They know the paleoseismic recurrence intervals. They can forecast the long-term hazard with reasonable confidence. What they cannot do, and what they openly admit they cannot do, is forecast the timing of the next major event in any practical short-term sense. The next major Cascadia rupture might be tomorrow morning. It might be in 3 centuries. The data we have does not narrow that window further than the paleoseismic record allows. This is, in some ways, harder to live with than either confident alarmism or confident dismissal. If the seismologists were sure the big one was imminent, we could prepare with conviction. If they were sure it was not imminent, we could relax. They are not sure of either, and they are honest about not being sure, and the result is that we live with a chronic background of small probability spread across long time windows. There is a particular methodological humility that comes out of the Haicheng-Tangshan pair that I want to spend a moment on, because it is foundational to how working seismologists approach mornings like this one. The 1975 Haicheng earthquake in northeastern China was a magnitude 7.3. It was preceded, in the months leading up to the event, by a sequence of observations that the Chinese seismological authorities interpreted as precursors. There were anomalous patterns in groundwater levels in wells across the region. There were reports of unusual animal behaviour. There was a foreshock sequence that built in magnitude over several days. The provincial authorities, based on the combined evidence, ordered an evacuation of the city of Haicheng on the day of the earthquake. When the 7.3 struck several hours later, the casualty count was vastly lower than it would have been if the city had been at its normal occupancy. The prediction was widely celebrated as the first major successful short-term earthquake prediction in modern science, and for several years afterward there was significant optimism in the global seismological community that systematic earthquake prediction was an achievable goal. Then, a year and a half later, in July of 1976, a magnitude 7.6 earthquake struck the city of Tangshan, less than 400 kilometers from Haicheng. There had been no evacuation. There had been no recognized precursor sequence. The Chinese seismological authorities, who had successfully predicted Haicheng the year before, did not predict Tangshan. The death toll was somewhere between 200,000 and 700,000, depending on which estimate you trust, making Tangshan one of the deadliest earthquakes in human history. The same monitoring system that had produced the Haicheng success had produced nothing useful for Tangshan in the same region, with the same instruments, run by the same scientists just a year apart. The lesson of the Haicheng-Tangshan pair has been absorbed across the global seismological community over the half-century since. The lesson is not that earthquake prediction is impossible. The lesson is that the precursor signals, when they appear, are not reliably present before all earthquakes of comparable size, and the absence of precursor signals before a given earthquake does not mean that the earthquake will not happen. The methodological consequence is that working seismologists treat foreshock-style observations with great care and significant skepticism, knowing that the historical record contains both successful predictions and equally significant failures, often in the same region with the same instruments. The morning's events at the Mendocino Triple Junction are exactly the kind of data that, in the post-Haicheng era, get watched carefully without being acted upon prematurely. The probability of being right about a foreshock interpretation in any specific case is not high enough to justify the costs of public action. The probability is not low enough to justify ignoring the events entirely. The honest position lives in that gap. There is one more piece of context that is worth offering on the modern state of operational hazard monitoring along the Cascadia margin, because it has improved meaningfully in the last decade. The Pacific Northwest Seismic Network, headquartered at the University of Washington, operates a dense network of broadband seismometers, strong motion sensors, and GPS stations along the entire Cascadia margin from Northern California up through Vancouver Island. The network publishes its tremor counts in near real time at the public Shake Alert and PNSN websites. The Shake Alert early warning system, which has been operational since the late 2010s, can detect a major earthquake within seconds of its initiation at the source and broadcast an alert to mobile phones and emergency systems before the strong shaking arrives at distant locations. The system is not a prediction system. It does not provide minutes or hours of warning, but it provides seconds to tens of seconds of warning, which is enough time for elevators to stop at the next floor, for surgeons to pause delicate procedures, for trains to begin slowing, for valves on natural gas lines to close, and for individuals to drop, cover, and hold on. The Cascadia margin in 2026 is the most heavily monitored subduction zone in human history. The probability that a major event would occur without immediate detection and warning is essentially zero. What is not zero is the probability that the warning, when it comes, will be the warning of an event that has already started, not the prediction of an event that is about to start. This morning's events do not change the long-term picture in any meaningful way. They are inside the range of expected baseline activity. The probability of a major rupture in any specific week, including the next one, remains very small. The slight conditional elevation produced by the morning's events, if it is real at all, is at most a few % on top of an already small base rate. It is not a reason to leave the coast. It is not a reason to cancel a trip. It is, however, a reason to remember that the long-term picture is the picture that matters, and that the Cascadia interface is not going to stay locked forever, and that whatever future morning brings the next major rupture will probably look something like this morning before it goes catastrophic. Part 10. The conspiracy theories the next week will bring. I want to take some time to walk through the alternative explanations that are going to circulate in the social media ecosystem in the coming days, because the pattern of these explanations is predictable, the physics of each one is wrong in specific ways, and a few of them sit close enough to legitimate science that they can mislead even careful viewers. The first claim that will appear is that the morning's earthquakes were caused by the High-Frequency Active Auroral Research Program, commonly called HAARP, the radio research facility in Gakona, Alaska. The claim takes various forms. Some versions argue that HAARP can target earthquakes through directed energy. Some argue that it modifies the ionosphere in ways that couple back into crustal stress. Some argue that the entire facility is a weather and seismic weapon disguised as research infrastructure. The energy argument against this is decisive. The HAARP facility operates at a peak, transmitted radio power of approximately 3.6 megawatts. a magnitude 5.7 earthquake releases an amount of energy that, when expressed in joules, is on the order of 10 to the 13th power. To put those two numbers in proper relation, the HAARP transmitter would need to operate continuously for many years to release the energy equivalent to a single moderate earthquake. And even if it could store that energy and release it instantaneously into the crust, there is no proposed mechanism for coupling ionospheric heating to fault rupture at depths of 10 to 20 kilometers beneath the seafloor 1,000 kilometers away. The atmospheric and electromagnetic perturbations produced by HAARP are confined to the upper atmosphere. They do not and physically cannot reach into the crust with anything like the intensity required to nucleate a rupture. The claim fails on energy budget grounds. It fails by approximately 15 orders of magnitude. The second claim that will appear is that the earthquakes were triggered by solar activity. This claim is more interesting because it sits adjacent to a small and ongoing scientific literature that has explored possible weak correlations between geomagnetic activity and shallow crustal earthquakes. The relevant papers include work by Duma and Ruzhin in 2003, and a more recent paper by Marchitelli and colleagues published in 2020 in Scientific Reports. Those papers do find statistically detectable correlations between certain measures of geomagnetic activity and certain classes of shallow earthquakes. The correlations are weak. The implied mechanism strength is in the range of 10 to the -9th or 10 to the -6th, relative to the tectonic stresses that actually drive rupture. The papers do not claim that solar activity causes earthquakes. They claim that there might be a weak modulation of unclear physical origin that could in principle bias the timing of events that were going to happen anyway. For this morning specifically, the solar seismic claim has a problem. The geomagnetic field this morning was quiet. The KP index, which is the standard measure of geomagnetic disturbance, was around 2 to 3 during the hours of the earthquake sequence, well below the threshold for any kind of storm-level disturbance. There was no geomagnetic storm happening when the earthquakes occurred. There was a solar flare cascade earlier in the morning, an M9.3 followed by an M7.7 followed by an X1, all from a single active region on the Sun. Those flares did produce coronal mass ejections, some of which may be Earth-directed, but the geomagnetic field had not yet responded to those ejections at the time of the earthquake sequence. The flares occurred at the speed of light. The coronal mass ejections will take 1 to 3 days to arrive. The geomagnetic field response is in the future, not the past, from the perspective of this morning's earthquakes. That timing makes the solar seismic causal claim for this specific event difficult to sustain. Even the most generous reading of the weak correlation literature requires the geomagnetic disturbance to have already arrived at the Earth before the earthquake occurs. It had not. Whatever causal effect solar activity might have on shallow crustal earthquakes, that effect cannot have driven this morning's events. The hypothesis is, in the language of working seismologists, honestly disconfirmed for this specific case. The third claim that will appear is some variant of the position that government agencies are concealing the precursors to an imminent Cascadia event. The form of this claim varies. Some versions argue that the USGS knows what is coming and is choosing not to alert the public to prevent panic. Some argue that the federal government has been quietly stockpiling resources for the Pacific Northwest event for years, while denying that they expect anything imminent. Some argue that the seismic instrumentation in the region is intentionally underdeployed to prevent the public from seeing the precursor signal directly. The structural counterargument to all of these claims is that the seismic data is open. The USGS earthquake catalogue is public. The Pacific Northwest Seismic Network publishes its tremor counts in near real time. The GPS data from coastal stations is downloadable by anyone who wants it. If the government knew something the public did not, the data they would need to know it is the same data that is available to any independent researcher in the world. There are independent seismologists in academic institutions across the planet who would, given the chance to be the first to identify a Cascadia precursor signal, publish that finding immediately. The scientific community is competitive in exactly the way that makes large-scale concealment of an imminent event practically impossible. The signal that the conspiracy claim depends on existing in someone's secret database does not exist in any of the public databases that anyone can look at. The most parsimonious explanation is that it does not exist in any database, secret or otherwise. The fourth claim, which sits adjacent to legitimate science in a way that makes it the most dangerous of the alternative narratives, involves what are called earthquake lights and pre-event electromagnetic anomalies. The peer-reviewed literature, in particular the 2014 paper by Saint-Laurent, Dare, and Freund in Seismological Research Letters, accepts that unusual atmospheric optical phenomena have been reliably reported in association with some moderate to large earthquakes. The phenomenon is probably real. The proposed physical mechanisms involve electrical charge generation in stressed rock as it approaches failure, with the charges propagating to the surface and ionizing the air above the source region. The literature is incomplete, and the mechanisms are not fully understood. The problem with the earthquake light's claim as a predictive tool is that the phenomenon is not reliably predictive. It does not occur before every earthquake. It does not occur only before earthquakes that turn out to be foreshocks. When it does occur, it is often only a few hours or minutes before the main event, which is too short for any practical action, and the reports are sufficiently anecdotal and visually variable that distinguishing real earthquake lights from ordinary atmospheric phenomena, from satellite flares, from lightning, from aurora, is extremely difficult after the fact. For this morning's events, no earthquake light reports were on the record at the time I'm putting this video together. If reports surface in the next few days from the Oregon or California coast, they will be worth examining carefully and skeptically. They will not by themselves be evidence of anything in particular. The fifth claim, which is worth mentioning briefly because it will appear and is worth dismissing efficiently, is that the morning's earthquakes were triggered by natural gas extraction, by deep injection wells, or by hydraulic fracturing operations somewhere in the Pacific Northwest. There are real cases of human-induced seismicity from these activities in other parts of the country, particularly Oklahoma and parts of Texas. The induced seismicity events have specific signatures. They cluster around injection sites. They have depths consistent with the depths of the injection horizons. They have magnitudes that are typically smaller than tectonic events, and that scale with the cumulative injected volume in characteristic ways. The morning's events have none of those signatures. They are far offshore. They are at depths consistent with tectonic Gorda plate seismicity. There is no high-volume injection activity within hundreds of kilometers of the epicenters. The induced seismicity claim is straightforwardly wrong for these specific events. The sixth claim, which is more recent in its current form but follows the same pattern as the others, will involve attempts to connect the morning's earthquakes to other geophysical events that happen to occur in a similar time window. A solar flare here, a coronal mass ejection there, an auroral storm somewhere else, a planetary alignment of some kind that someone will diagram and post to a forum. The pattern of this kind of claim is to identify events that happened roughly simultaneously, and to assert a causal connection between them on the grounds of the simultaneity alone. The technical name for this fallacy, in the philosophy of science literature, is post hoc ergo propter hoc, which is Latin for after this, therefore because of this. It is one of the oldest recognized errors in inductive reasoning, and it is by far the most common error that appears in social media discussions of earthquake causation. Two things happening close together in time does not imply that one caused the other. The Earth is a busy place. Thousands of small earthquakes happen every day. Tens of solar flares happen every month. Hundreds of meteorites burn up in the atmosphere every week. The probability that any given large event coincides with some other notable event within a few hours or days is essentially 1. The fact of coincidence by itself contains no information about causation. The morning's earthquakes will certainly have coincidences with other events. None of those coincidences will mean anything. The seventh and final claim category, which I want to address because it is the most insidious form of the alternative narrative ecosystem, involves the broad framing of seismic events as part of some larger pattern of geological or cosmic acceleration. The claim takes many forms. The Earth is entering a new phase of activity. The poles are shifting. The magnetic field is collapsing. The grand solar minimum or maximum is reorganizing the crust. The galactic plane is doing something. The Sun's binary partner is approaching. The various forms of this claim share a common structural feature. They propose that the recent past represents the early stages of a planetary scale change, and they invite the listener to interpret each new earthquake or eruption or storm as a confirmation of the larger pattern. The seismicity data does not support any of these framings. The global earthquake rate, when properly normalized for the improvements in instrumental coverage over the past century, has not increased. The rate of magnitude 7 and greater earthquakes globally has been roughly constant for as far back as the catalogues go. The rate of magnitude 8 and greater earthquakes has fluctuated by random walks of a few events per decade in either direction, without any directional trend. The geophysical evidence for a planet-scale acceleration in seismicity does not exist in the modern catalogues. The framing relies entirely on selective memory of recent events, and on the human cognitive tendency to perceive patterns in random sequences. For this morning's events specifically, no such broader pattern is required to explain them. The Mendocino Triple Junction produces moderate earthquakes constantly. This morning's were within the normal range. They do not need any larger cosmic story to make sense of them. The general posture I want to leave you with on the conspiracy claims is that the genuine uncertainty in the data, which I have tried to be honest with you about throughout this video, is interesting enough on its own that there is no need to import additional speculation. The Cascadia interface is loaded. The Mendocino Triple Junction is active. The morning's events are at the upper edge of normal. None of those facts require any hidden actor or any unknown mechanism. The geology by itself is enough. Part 11. The week ahead. What should you, as a person watching this video on the evening of June 3rd or the morning of June 4th, actually expect over the coming days? The most likely outcome, by a substantial margin, is that nothing further of note will happen. The seismicity rate at the Mendocino Triple Junction will return to baseline within the next 24 to 48 hours. The petrolia events will be relocated to more conventional depths, and the catalogue will be cleaned up. The Pistol River 5.7 will be the largest event in the regional catalogue for some weeks. By the time we get to the end of June, the morning sequence will be a routine entry in the USGS database, and the public attention to it will have moved on to whatever the next story is. This is the baseline. It is what happens in roughly 9 out of 10 cases of moderate offshore Mendocino sequences. It is what I expect. A less likely but still plausible outcome is that the sequence will produce additional moderate events over the coming days. Aftershocks from the Pistol River 5.7, secondary events triggered by the stress transfer on adjacent Gorda Plate faults or on the Pacific Plate side of the Mendocino Fracture Zone, additional cluster events in the Petrolia offshore region. The magnitudes would probably remain in the 4 to 5 range. The pattern would be characteristic of an aftershock decay, with the rate dropping off according to the standard Amori law. This is the kind of activity that historically follows a moderate Mendocino sequence. It would not be a cause for alarm. It would be the system completing its routine response to the morning's events. A small but non-zero possibility is that the sequence will produce another moderate to large event on an adjacent structure. The most plausible scenarios involve either a strike slip event on the Pacific Plate side of the Mendocino Fracture Zone, in the way that the 1992 7.2 triggered the 7.5 and 6.6 aftershocks, or another internal Gorda Plate event further north or further south. An event in the magnitude 6 range somewhere in the Triple Junction region within the next week would not be unprecedented, and would not, by itself, indicate that anything larger was about to happen. It would simply be another piece of the same regional activation that started this morning, a very small but not zero possibility, and the one I want to be most careful about how I describe, is that the morning sequence is the early stage of a precursor pattern, preceding a major rupture on either the Cascadia interface or the northern San Andreas. The probability assigned to this outcome by the available data is in the range of a few percent. It is not zero. It is also not large. The reason this possibility is worth describing carefully, rather than dismissing or amplifying, is that the consequences of this outcome being correct would be significant enough that people who live in the affected region should be aware of it as a possibility, while not changing their daily lives on the basis of it. The practical advice is the same advice that the Oregon Office of Emergency Management and the California Office of Emergency Services have been giving residents of the coast for decades, which is to maintain the standard preparedness baseline. Have water, have food, have a plan for where to meet your family if cell service goes out. Know the tsunami evacuation route from any beach or coastal park you visit. Know that the inundation zones in Crescent City, Eureka, Coos Bay and points along the Oregon coast have been mapped in detail, and that the signs marking the routes to high ground are real and the routes are well tested. The standard preparedness baseline does not change because of this morning's earthquakes. It is the standard baseline because the regional hazard does not change much from year to year, and the morning's events do not significantly change it either. What I will be watching for in the days ahead, and what I will report on if it develops, are several specific things. I will be watching the southern Cascadia tremor count from the Pacific Northwest Seismic Network. If the tremor count remains elevated or increases over the coming days, that would suggest that the southern segment is in a more actively loading state than the baseline, and the conditional probability of follow-on events would be slightly elevated. I will be watching the GPS stations along the southern Oregon and northern California coast for any sign of anomalous motion that would indicate slow slip activity on the deeper Cascadia interface. I will be watching the regional seismicity rate at the Mendocino Triple Junction. If the rate stays high for more than 72 hours, or if events start to migrate spatially in a coherent direction, those would be features of the data that would warrant closer attention, and I will be watching for the standard set of false signals that often accompany high-attention earthquake periods. Reports of unusual animal behavior, reports of dramatic well water level changes, reports of strange atmospheric phenomena. Most of these reports turn out to be either unreliable, unfalsifiable, or completely unrelated to the seismicity. I will not be amplifying them unless they reach a level of confirmation that meaningfully distinguishes signal from noise. There is a particular kind of attention curve that follows events like this morning's, and it is worth describing because it changes how the regional public discussion is going to evolve over the next 10 to 14 days. In the first 24 hours, the events appear in the technical seismology feeds and in a small number of attentive news outlets. The audience for that coverage is largely the people who already follow these systems closely. In the next 48 to 72 hours, the events are picked up by a wider tier of regional news outlets and by the algorithmically driven content channels that aggregate seismic activity, and the public discussion broadens to include some fraction of the general population that lives along the affected coast. In the 4 to 7 day window, if no follow-on events have occurred, public attention begins to decline rapidly. By the end of 2 weeks, in the absence of further events, the morning will be effectively forgotten outside of the technical community. That attention curve is predictable, and it is one of the reasons that operational earthquake forecasting is so difficult as a public communication exercise. The window during which the public is paying attention is the window during which the data is most ambiguous. By the time the data has resolved into either a routine outcome or a follow-on event, the public has either moved on or is reacting to the new event, and the careful interpretive work that should have been done during the ambiguous window has often not been done. What I would like to encourage, for the small fraction of you who will keep paying attention through the next several days after the news cycle has moved on, is to maintain a calibrated awareness of the system without letting that awareness tip into either complacency or panic. The Cascadia margin is not going to fail this week. It is also not going to remain locked forever. The probability of failure in any specific week is small. The probability of failure in any specific century is, eventually, large. The morning's events are a small piece of data in a long ongoing story. They do not require you to do anything different today. They do not justify any specific change in how you plan your week. They are, however, a small invitation to remember that the long-term picture is real, and that the kind of preparedness that makes sense for the long-term picture also makes sense whether or not anything dramatic happens in the next several days. Water, food, a communications plan, a meeting place, knowledge of the local evacuation routes. None of these things are specifically responsive to this morning. All of them are appropriate to the place where you live. There is one more thing I want to mention before we close out this section, which is the question of how to think about probability when the consequences are asymmetric. The morning's events have approximately a 5% or smaller probability of being foreshocks to a larger event in the next week. That number is small. If you were betting at those odds, you would bet on the routine outcome essentially every time. But the consequences of the routine outcome being correct and the consequences of the foreshock outcome being correct are dramatically different. If the routine outcome is correct, nothing further happens. If the foreshock outcome is correct, a major rupture occurs on the Cascadia interface, or the northern San Andreas, with significant casualties, billions of dollars in damage, and consequences that reshape the Pacific Northwest for decades. The expected value of preparing for the small probability event is therefore larger than the expected value of preparing for the most likely event, because the consequences of being unprepared for the small probability event are so much larger. This is not a recommendation that you panic. It is a recommendation that you keep the standard baseline of preparedness that the Pacific Northwest emergency management agencies have been recommending for years. The standard baseline is not expensive. It is not disruptive. It is something you do once and then maintain in the background while you live your normal life. The morning's events are a reminder to check, if you have not checked recently, that the standard baseline is in place. They are not a reason to do anything beyond that. Part 12. The clock that does not stop. Let me end with what I started with. A magnitude 5.7 struck 138 kilometers west of a small Oregon town in the pre-dawn hours of June 3, 2026. Within the next 2 hours, a cluster of moderate events struck offshore Petrolia, California. The events happened at the corner where the Pacific, North American and Gorda plates meet. They happened on the same plate boundary system that last produced a catastrophic rupture in the night of January 26, 1700, when the Cascadia Subduction Zone failed completely and sent a tsunami across the Pacific that arrived in Japan less than a day later. As of this morning, 326 years and 4 months have passed since that night. The southern segment of the Cascadia interface has been quiet for that entire stretch. The Gorda plate that sits on top of it has been internally deforming the whole time, generating its own constant background of small to moderate earthquakes, of which this morning's sequence is the latest. The events this morning, taken at face value, are routine. They are at the upper edge of routine, but they are routine. They are most likely the random pulse of a chronically active region, and they will most likely dissipate without further consequence. The data on the table does not support an interpretation of imminent danger. The data does support an interpretation of legitimate uncertainty, and I have tried to walk you through that uncertainty honestly, without either dismissing it or amplifying it. What you should take from this video, more than any specific number or fact, is the recognition that the Pacific Northwest sits on a clock that we do not have the technology to read precisely. The clock has been running for 326 years and 4 months. It will keep running. We do not know how much longer it will run before it strikes. We know it will strike at some point in the future that is more likely to be within the next 2 or 3 centuries than to be outside of them. We do not know whether the strike, when it comes, will be preceded by a recognizable pattern of warning events, or whether it will arrive on an ordinary morning with no notice. The events this morning may be the first warning, or they may be nothing at all. The data cannot tell us which. I want to spend the last few minutes of this video on something that does not get said often enough about Cascadia, which is that the unique fact about the 1700 event is not its size. There have been earthquakes larger than 1700 in the historical record. Chile in 1960 produced a magnitude 9.5, the largest instrumentally recorded earthquake in human history, and the rupture geometry was broadly comparable to a full-margin Cascadia event. Sumatra in 2004 produced a magnitude 9.1 or 9.2 with a rupture that extended for over 1,000 kilometers along the Sunda megathrust. Japan in 2011 produced a magnitude 9.1 on the Japan Trench. The Cascadia event was probably comparable to any of these in size. What is unique about it in the modern context is that it happened to a populated coastline before that coastline was instrumented. The 8 or 9 other comparable subduction zone events of the past few centuries all happened either before modern instrumentation existed at the location, in which case we know them only through ancillary evidence the way we know Cascadia, or after modern instrumentation existed, in which case we have detailed records of what they did and how they failed. What that means for Cascadia specifically is that the modern Pacific Northwest is, in some real sense, due for an event that has never happened in the modern era at any subduction zone. The next Cascadia rupture, whenever it comes, will be the first major full-margin subduction zone event in the modern instrumental era that occurs at a coastline with dense modern population, modern infrastructure and modern emergency response systems. Sumatra in 2004 affected coastlines that were less heavily developed than the Pacific Northwest. Japan in 2011 affected a coastline with extraordinary preparation, but also with infrastructure vulnerabilities that the rupture exposed. Chile in 1960 affected a coastline that was less densely populated than the Pacific Northwest is today. The next Cascadia event will be the first of its kind to test what modern civilization can absorb from a full-margin subduction zone rupture. It will be the test case. The morning we just had may or may not be the first whisper of that test arriving. That is the long view. It is the view that the seismologists who study this region carry with them every day. It does not mean they expect a rupture tomorrow. It does mean that they understand the 1700 event as not a curiosity in the historical record, but as the most recent example of a process that has been going on for millions of years and will continue going on for as long as the Pacific Basin exists, and that the modern world has not yet had to absorb the next iteration of that process. When it does, the morning before it happens will probably look much like this morning. Small offshore events, no warning, no headlines. The clock continuing to run quietly. What the data can tell us is that the place where it will happen is exactly the place where this morning's earthquakes happened. Not on the Cascadia interface itself, which is the locked patch underneath North America, but adjacent to it, on the system of plates and faults that surround it and that load it slowly toward failure. The Gorda Plate, the Mendocino Triple Junction, the Mendocino Fracture Zone, the southern terminus of Cascadia, and the northern terminus of San Andreas. The earthquakes this morning happened in the right neighborhood. They happened on the right system. They happened at the right time of the cycle, 326 years into a recurrence interval, that is, for the southern segment, in the range of 200 to 530 years. The clock keeps running. Whatever future morning brings the next Cascadia rupture, the days and hours before it will probably look much like the morning we just had. A moderate earthquake in the night, a small cluster offshore, a modest entry in the USGS catalogue, a few hundred did you feel it reports, no tsunami warning, no damage on land, and in retrospect, after the fact perhaps, the first thread of a pattern that no one was certain they were seeing while they were seeing it. That morning may come tomorrow, it may come in a year, it may come in a century. The honest position is that nobody knows, and the people who claim to know are usually selling something. The data this morning is interesting. It is not alarming. It is also not nothing. It is exactly the kind of data that the Pacific Northwest will continue to produce, in small and middling doses, for as long as it takes for the locked patch underneath the continent to give way. The locked patch is going to give way. That much we do know. When and on what timetable and with what warning, we do not. For the next 24 to 48 hours, the most likely thing in the world is that nothing further happens. The catalogue will quiet down, the morning's events will be relocated, magnitudes refined, mechanisms determined, the aftershock sequence will play out and decay, the coastal communities will go about their business, the fishermen at Crescent City will go out for their boats, the morning commuters on Highway 101 will drive their commutes, the clock will keep running, the way it has run for 3 centuries and 4 months, and the next time the corner cracks, we will all be exactly where we were this morning. Asleep, or working, or driving, or making coffee, while a few hundred kilometers off the coast a small piece of the earth rearranges itself in the dark. Stay watchful, stay prepared. The geology is going to do what the geology is going to do, and the only piece of it that is in any of our hands is the part where we prepare without panicking, where we take the standard precautions without becoming consumed by the fear of a future event that may or may not arrive in any specific frame of our lives. The morning was a reminder. It was not a warning. It was the geology speaking quietly, the way the geology has been speaking quietly for 326 years and 4 months. We will keep listening. We will keep reporting. And when the next pulse comes, on whatever future morning it comes, we will be here to walk through it with you the same way we walk through this one. There is a particular comfort sometimes in remembering that the Earth has been doing this for billions of years before any of us arrived, and will keep doing it for billions of years after we are gone. The Cascadia margin will rupture, and the cycle will continue, and the new oceanic crust forming at the Gorda Ridge tonight will eventually be shoved underneath North America in some far future moment that none of us will live to see. The work of those of us alive right now in the year 2026 is to be the species that knows about the process, that can describe it accurately, that can prepare reasonably for what it will eventually do, and that does not lose its head in the meantime. The morning's events do not by themselves change any of that. They are a small reminder. They are not a turning point. The clock keeps running. Stay safe. The clock keeps running. So do we.